So good day everyone. Today we're gonna try to answer those questions coming from my midterm exam. So here's the questions, some of the questions. Let's start with number 1. It says that express the Boolean function f is equal to a or b prime c as a sum of minterms. So let's take note here, it is a sum of minterms. So here we're just gonna rewrite this function here. F is equal to a or b prime c. There you go, as you can see. So here, as you can see, those minterms are missing in literals. So we're just gonna multiply these minterms. First is a, multiply it by b or b prime. So why is it b or b prime? This b or b prime will just be equal to 1. So if you multiply 1 by a, this will go back to a. So it's just the same. So the use of this is just to complete the number of literals for each minterm. So here we have next the OR of b prime c multiplied by a or a prime because it is missing a literal of a. So by distributive property, we have ab or ab prime or a b prime c there or a prime b prime c. So this is again, it still lacks one literal. Okay, so we have to multiply these two minterms by c or c prime. So we have ab c or c prime or ab prime c or c prime. Then just write these two leftovers, a b prime c or a prime b prime c. So by distributive property again, let's just distribute this one, a b c or a b c prime or a b prime c or a b c prime. I'm sorry, a b prime c prime. That's correct. Then a b prime c or a prime b prime c. So as you can observe, there are two minterms that are the same. So these two minterms will just be simplified, okay, into just one minterm only. Let's just copy the rest. So the final answer would be ABC or ABC prime, or these two terms will be cancelled, will become one. So that becomes A B prime C or A B prime C prime or A prime B prime C. So there you go, we have there the final answer. Next question will be number 2. Express the Boolean function f is equal to x, y, or x prime z as a product of Maxterms. So here we have to take note the product of Maxterms phrase. So here we're just gonna write this function as f is equal to x, y plus x prime z. Now I assume that you know that the sum of minterms are the terms in which the output will be equal to 1. The product of Maxterms constitutes to the output that are zeros. Okay, so here, since this lacks a literal, these two minterms lacks literals, we have to do the same what we have done in number 1. So we have to multiply this xy by, it lacks z, so we have to multiply it by z or z prime, and then copy or x prime z. This lacks a literal of y, so we have to multiply it by y or y prime. There you go. So this becomes, by distributive property, let's just distribute x y z or x y z prime or x prime y z. Is it correct? Okay. Then or x prime y prime and then z. Now this function, as you can notice, is in the sum of minterms form. So let's convert this into the product of Maxterms. If we convert, these have the outputs of 1. So if we convert, the invert of this will have a complement, will have an output of 0, and that is the product of Maxterms. So we complement this function. This becomes f prime is equal to xyz or xyz prime or x prime yz or x prime y prime z, and then complement the whole function. By complementing the whole function, we use the De Morgan's theorem. Okay, so f prime is equal to xyz prime, and then the or becomes an end right here, xyz prime, then prime that one, and then with x prime yz prime, and then with x prime y prime z, then lastly prime that last midterm. Okay, now simplify this, distribute the primes, okay, to the literals. So we have that f prime is equal to x prime, or because the inside has operations of ends, okay, since we are complementing it, we have to change it into an or operation. So we have, and the terms inside are inverted or complemented. So each are complemented. So we have x prime or y prime or z prime, ended with x prime or y prime or z, and then a third ended with x or y prime or z prime, and then lastly we have x or y or z prime. Now this is what you call the product of max terms. These are the max terms and they are ended, so they are called the product, and this is the final answer, product of max terms. Okay, for the third problem, we have here NAND and NOR gates are called universal gates. Okay, let's prove that. Show by drawing that AND, OR, and NOT can be implemented using NAND and NOR gates only. So here we have the AND, or the AND, here, the OR, and the NOT. So what we're gonna do, we're gonna implement these three gates using the NAND and NOR gates only to prove that they are called the universal gates. Okay, so first, by using NAND gates, okay, this is an inverter or a NOT gate. Okay, by using a NAND gate, this can be an inverter. Okay, so we have an input of A. What we're gonna do is we're gonna assume that we have a 2-input NAND gate. So it has a 2-input AND gate, just like this. There you go. What you're gonna do, you're gonna short these 2 inputs as one. So we have 1 input, it's A. Okay. So the output of this NAND gate, okay, A implemented or complemented is an A prime. So simple as that. Okay. Next, we're gonna use NAND gates to implement an AND gate. Okay. So here, again, we're gonna use 2 inputs A, B. Okay. So these 2 inputs are fed into a NAND gate. There you go. Observe the result of this one. So A and B prime. A, B prime. But the result should be AB. So we're just gonna complement this again to go back to the original answer. So complement this just like what we did in the first example. We're gonna invert this output by using a NAND gate again. So the prime will be cancelled and it will gain an AB as a result. Okay. Lastly, we're gonna use a NAND gate to prove an OR gate. Okay. So first, we're gonna use one NAND gate to implement or to complement each input. here we have an A as an input and B as an input. So the first thing we're gonna do is we're gonna implement first the A and the B. Okay. This gives a result of an A prime and a B prime. Okay. This A prime and B prime are then fed into another NAND gate. Okay. And this results to a function A or B. Okay, let's explain this one. An A prime and B prime that are NAND are ended with a prime. There we go. So by using De Morgan's theorem, we're gonna have A. Okay, distribute the prime here. This becomes A, and there's an AND operation there that becomes an OR, and distribute this again. This becomes B. So it has been proven. Next, we're gonna use NOR gates to prove. Okay, NOR gates. Again, NOR gate can be used also as an inverter. So just simply short again the inputs of a NOR gate. Okay, and this results to an A prime. So it functions as an inverter in that way. So next, we're gonna use NOR gates to implement AND. So first, we're gonna use the OR gate to complement the input. This becomes A prime. Okay. And then here, I have another inverter. This becomes B prime. Okay. So if we feed these two prime inputs into another NOR gate, what will happen is that will be ended AB. So here's why. A prime, B prime, take note the prime, this one and this one are the same. Okay, don't be confused with it. So if we OR NOR them, I'm sorry, this is OR there, by using the De Morgan's theorem. Okay, distribute the prime, this becomes an A, the OR becomes an AND, and the B prime becomes B. So we have the same result. Okay, and lastly, we're gonna use NOR gates to implement OR. Okay, so you have A, B. Okay, we're just gonna feed these two inputs into a NOR gate. Okay, so what will happen? This will become A or B prime. So we have, or we want a result A or B, but there is a prime, so we're just gonna feed it into another NOR gate to cancel the prime. This becomes A or B. Okay, moving on for our question number 4. Here it states, create a simplified expression for the following output. So here we have a function. Okay, the output here means that the output of the function is a logic one. Okay, so here it is logic 1 in Minterms 0, 1, 2, 3, 6, 7, 8, 9, 10, 12, 14, 16, 18, 20, 22, 23, 24, 29, 30, and 31. So those numbers have outputs of 1. So here it states that we solve this, okay, function, or we simplify this expression using Karnaugh map. Next, we create the circuit diagram, and then lastly, we make the truth table so that we can look at the outputs here, or we can prove that they are right. Okay, so first we're just gonna write ones for the logic ones. Here in 0, we're just gonna write here 1. This constitutes to 0 here. This is a 0. M0, M1 is a 1. M2 is here. That is a 2. And M3 is also a 1. Okay, let's just pause in there. I'm gonna discuss to you these Karnaugh boxes. Okay, these Karnaugh boxes are used to simplify expressions. This one is a 5-variable Karnaugh map. Okay, so the first box constitutes the A prime, and the second constitutes the A. Here, these two rows here constitutes to be the same in here. This C here constitutes to this rows in here, the same in here. The D constitutes to these columns, 2 columns, the same here. And also the E constitutes to these columns in between, the same here. Okay, let's resume what we've done here. So in 0 we have 1, in 1 we have 1, logic 1, in 2 we have logic 1, in 3 we have logic 1, in 4 we have no 4 there, so that is a logic 0, 4 is here, a 5. So here we can see that the 4 is not included in the function, so it is a 0. Next, we have a 5. There is no 5 in there. Okay, so it is a 0. Next is a 6. Okay, 6 is a 1. 7. We have a 7. And the next, the 8 is here. Okay, 8. We have an 8, so let's put 1. A 9. Okay, a 10. This is a logic 1. We have a 10 in there. No 11, so this is a 0. We have 12. 1. 13, no 13, so that is a 0. 14, it's a 1. And there is no 15. So that is a 0. As you can observe, we have here the zeros. Okay, 0, 1, 2, 3. Take note with that. 4, 5, 6, 7. Okay, there is a pattern. 7, and then 8 in here. 8, 9, 10, 11, 12, 13, 14, and 15. Okay, those constitutes to the minterm or minterms, okay, of the different inputs, different input combinations. So we've ended in 15. The 16 here is in the next box. Okay, 16. By implementing the same pattern here, 16 here, we have a 16, that is a 1. No 17, 0. An 18, 1. 19, no 19. We have a 20. No 21, 0. A 22. We have 22, 23. A 24. No 25. No 26. No 27. No 28. There is a 29. There is a 30 and a 31. Okay, now that our Karnaugh map is now completed, we're gonna make the function now. So here we're gonna look for a the logic output that have ones that are located in sides, or let's say we're gonna look for the adjacent outputs that has 1. So here we can see there are 4 adjacent ones. Here also we can see there are adjacent ones forming a square. These are also adjacent ones. these two ones are also adjacent at each other. Okay, as long as they're in the corner of the square. These ones here, the two ones here, are also adjacent with the two ones in here. And so it's the same with the two ones in here at the side are also adjacent with the ones in here. Now what we're gonna do with the adjacency rule that is implied in here is the same with the second Karnaugh box. The thing is, or the other thing is that the adjacency is that this one is also adjacent to the corresponding one in this box. The same with the one here, this one here as adjacent to the one in here. Okay. Lastly, the one in here is adjacent to the one in here. Okay, the technique is that we're gonna find the most number of ones that are adjacent. Okay, so let's see. We have here in the first box. Okay, so here we have these 4 adjacent ones. Okay, these 4 adjacent ones are located in the box of A prime. So we're gonna write this one as A prime. Next, we have B. They are not located into the B, but they are located into the B prime. Okay, this is the B prime. So that is a B prime. The C. The ones are in the half of the C. There are no ones in the half of the C. So that cancels it. Okay. Here we have the D. The ones or the 4 ones are located into the D. So we're gonna write it as D there. The E here, okay, just gonna write it here. The half of the 1 are in the E, but there are no ones constituted to this group. So that cancels the E. Okay, I hope you get it. So next, we're just gonna repeat that what we've done until we finish all of the ones, or we get rid all of them. Okay, or in other words, we have partnered them with their adjacent ones. Okay, so the next is we have here ones in here are adjacent with the 2 ones in the bottom. Okay, again, this is found in the box A prime. They are not found in B alone, but they are found also in B prime, so that cancels it. The C is these 2 rows. They are found in C primes. Okay, C primes, so we're gonna write C prime. Okay, the D, they are not located in D, but they are located in the D prime, so we're gonna write D prime. In E, the 2 ones are located in E, but there are no ones located in E regarding these 2 adjacent, so that cancels it. I hope you get the pattern, and that goes on and on until we get rid all of the ones. Next, we OR this. Okay, we have here these 2 adjacent squares are also adjacent with the squares or the ones here this side. Again, this is found in box A prime. They are also found in the B. Okay, the C, there are 2 ones in the C, but there are no 1 on the other side. The 2 ones are in here, not in here, so the C cancels. Okay, in D, there are 2 ones in D. There are 2 ones also in D prime, so the D and D prime cancels. Okay, and lastly, the E, there are no ones located in E because they are both outside the E, so this will be E prime. Okay, so the technique is that you're gonna find what literal are they in, or the ones are in. They're inside the B, so you put it in here in the minterm. Okay, that's the technique in there. So we've got rid all of the ones in the first box. Let's proceed to the second box. Okay, here we have let's see, we have here 4 ones, adjacent ones. Okay, there we go. It constitutes, or it is found in the box A, but they are found in B. They are found also in B prime. Okay, B prime, so that will be cancelled. They are found all in C, so let's write C. They are also found on the D. They're all found in D, so let's write D. The 2 ones are found in E, but there are no ones found here in this column, or the 2 ones are in E prime. So E or E prime is a 1, so that cancels it. Okay, so the next is we have, let's see. Okay, I'm sorry, this is a C. Okay, it's not C prime. Okay, sorry, that is a C. Next we have 2 adjacent squares and 2 adjacent squares. There we go. They are all found again in the box A. If this is the B, this is the B prime, they are all found in B prime, so let's write B prime. The C, we have 2 C's, but the other 2 are C prime, so that cancels. The 2 are D, but the other 2 is in D prime, so that cancels. There are no E's, but they are both in E prime, so let's write E prime. Okay, and then next we have here, you have here a 1. So this one and this one, these 2 ones are adjacent to the ones in this other box. Okay, so why did we choose to partner these 2 again with these 2? This is necessary to use a less number of literals, okay, or to simplify, because if you're gonna write the minterm of this one, it takes too much literals. So in simplifying a Boolean expression, we always want to use less literals. Okay, so they are both found in A prime and A, so that cancels it. They are also found in B and B prime, so that cancels it. Okay, they are found not in C but in C primes, so we write C prime. They are not found in D, but they are found in D primes. Okay, let's write D prime. And then they are not found in E, but are found in E prime. Just write E prime. Lastly, we have the one in here. It's not partnered with anyone in there. Okay, so the last resort is to partner this one with this one. It is okay to use the adjacency rule even if the one is used. Okay, if this one is used, it is okay to partner it again with this one, just for the simplification. So again, it is found in A, in B, in C. It is found also in C. The other one is D, but the other one is in D prime, so that cancels it. But they are both found in E, so let's write it. Okay, what we're gonna do is we're gonna use the distributive property to factor out these terms. So I'll factor out the A prime here. Okay, the first min term, we have B prime or D. We have factored out the A prime. Next, we have factored out the A prime. So what's left is C prime, D prime. And then lastly we have B, A prime. Then we'll factor out. We have commons here, A and C. So that leaves B or B, A. And lastly, we have common A prime. Okay, I'll put underlines. A prime as common, literal, A, B prime, or C prime, D prime. So that will be the final answer. So for the circuit diagram of the problem number 4, this is the circuit diagram. Okay, we're just gonna implement the minterms in the Proteus. I'm using Proteus. So as you can see, that is the circuit diagram, and the truth table is here. Okay, so the minterms that are found, okay, are simplification. So the function is a is a 1 in 0. It is also a 1 in 1. It is a 1, logic 1 in 2. It's logic 1 in 3, and so on and so forth. So that is the truth table of it. Okay, there you go. Okay, for the last problem number 5, let's create the truth table for the hexadecimal to 7 segment that will display hexadecimal number from 0 to F from every combination of 4-bit input. Okay, so as you can see, here we have the truth table. Okay, so the binary inputs, these are the inputs. 000 stands for a 0 on the 7 segment display. So on the 7 segment, okay, we have a 0. So before we tackle this truth table, let me discuss to you the 7 segment display first. So this is the 7 segment display that we're gonna discuss. Okay, it is called 7 segment display because it has 7 segments: first, second, third, fourth, fifth, sixth, and the 7th segment. So the first segment is an A, the second is a B, the third is a C, fourth D, E, F, and then lastly the 7th segment is the G. Okay, so if we want to display a 0 in here, we're gonna use these segments right here. Okay, except for the G. Okay, except for the G. So I hope you understand it. This will only light. Okay, that constitutes to a 0. Okay, except for the G. So it means that the logic of A will be 1 because it will light up. The logic of B will be 1 also, and also with C, D, E, and F, except for a 0 that has a logic 0. Okay, if we want a 1 to be displayed into the 7 segment display, we're gonna use only the B and C. Okay, so that means that the B and C will only light up. So they are in logic 1. B is in logic 1, C is in logic 1, and the rest are all logic zeros. Okay, last example, we have number 2. Okay, number 2 uses A, B, G, okay, E, and D. So it means that A, or if we want to display 2, the A is a logic 1, B is also logic 1, C is a logic 0, okay, D is logic 1, E is logic 1, F is logic 0, and G will also be used, and so it is logic 1. And for the last or the remaining displays, I hope you get how it is done, and I want you to do it as an exercise for you. Okay? So back with the truth table. The complete truth table for the 7 segment display is here. Okay? So that is from 0 to 9, A, B, C, D, E, and F. Okay? I hope that you got the correct answers. Okay? If you want to compare your answers with the correct ones, just compare it with here. Okay? There you go. And that ends my midterm exam. I hope that you like my presentation. That's all, and thank you very much for listening.